Hello, welcome to part 2 of our drunk programming series. Last time, if you didn't see, we coded this. Let me run it for you. This chess game, you see we start with the board. It's got letters, numbers to show you which row and file you're on. We can play, for example, e2 to e4. You see our piece actually moves. Now it's black's turn. So black can now play like e7 to e5 and so on. And you can play a whole chess game like this. The shortcomings are that there's no move checking, no checkmate or endgame condition, and there's no castling. And there's also nothing in place to make sure that white can only move white pieces and so on. But since the pieces are annotated with the W and a B, and since we have this curve turn or curve player variable that determines whether or not the curve player is white or black, if you want to add that on your own, it shouldn't be too complicated to actually put the logic in to make sure that white can only play white pieces on their turn. Okay, so that was last episode. If you want to watch that, go check it out. But this, I said that we'd sort of step up in complexity at each step. So this time, I think what could be fun is this time if we do something a little more theoretical, a little more academic, and we do a binary search tree from scratch. We're not going to reference the internet at all, so this should be fun. Let me just turn the music down a little bit. Okay. So, binary search tree. I'm going to use this. So what is a binary search tree? It's a data structure with nodes and edges, right? So let's say this is 4 to 6, right? So we have nodes and we have edges, and there's a rule. So you see this node and has these two coming out of it. This is what we call a parent node. And a parent node just means that it's a node who has what we call children, right? So this could be the parent node and these could be its two children right here, right? So the rules of a binary search tree are that a parent node can have at most two children, so it couldn't have a third child coming off here. And also a child off to the left is always going to have a value smaller than its parent, and a value to the right is always going to have a value greater than its parent. So if I had, for example, this, that would not be valid because a child to the left of its parent also always has to have a value smaller than its parent. So as long as this is smaller than 4, this is good. So let's say 3 here. Okay, so that's the basic idea of a binary search tree. Alright, so we're going to code this from scratch, and really what I hope to be able to do is, let's actually write this in the code editor. So episode 2, binary search tree. And what we hope to do is creation, insertion, traversal. We'll just focus on like in order traversal for now, and deletion. And goals. Okay, so again, we're making a binary search tree, and our goals that we can create, insert, traverse, and delete from our binary search tree. Okay, so I just finished one. We're going to open up our second one. Let's clear our terminal. And now we have to think what makes up a binary search tree. So like we said, we have nodes, right? And we have children for those nodes. And this is essentially, if you're familiar with programming, this is going to be a pointer. Okay, so this is a pointer from this node to this node. So we have nodes and we have pointers to other nodes. Okay, so why don't we start by defining a node itself. All right, so each node is going to have what's called like a value, and it's going to have a pointer to its left and right child. Okay, so let's say class tree node will have a value, it will say self.val is equal to val, not that, self.left is equal to left, is equal to right. And this needs to go inside of a constructor function. Okay. And let's create some getters. Let's just say, just to follow best practice here. Good. So let's say def set value, self value, self.val is equal to value, def get value, self value. We don't need a value parameter. Return self.val. Okay. Def set left self left child. Self.left is equal to left child. Def set right self right child. Right self.right is equal to right child. Okay. So now we have a basic node data structure where we take in a value, we initialize that node, and later we can get the value, set left and set right nodes. I don't think there's really any need to, I don't think there's, oh my god, there's so many pop-ups coming up. Okay, I don't think there's any need to get the left and right children of a node. We can just access them using this left and right, since I don't know if in Python we can set private variables, but we just won't worry about that for now. Okay, so now we have a node class where we take care of what we were hoping to take care of. We have a node, right? We have a node data structure with a value, and then it has pointers to its left and right child, right? And these will be other tree nodes if we, for example, want to insert a node underneath this for node. Okay. I'm being spammed on WhatsApp, same as last video. Okay. So now let's create a class called a tree, right? Def init self, right? And I think the only thing we need to start a binary search tree is a root. Self.root is equal to none. So we'll say def set root self.root. We call this root node equals root node. Okay, so now we can create a tree by creating a node and then creating a tree and passing it a root node that we want to start with. So we'll create a node and then we'll create a tree using that node that we created, and that will become the root of our tree, our starting point. Okay, so again, our goals were creation of binary tree which we've now done because we can take a node and set the root of our binary tree to that node, and then from there we can simply use our node objects to add children to those nodes. Okay? So now let's do insertion. So let's call def traverse self. If not self.root, meaning if our tree doesn't have a root, if this for node doesn't exist, and for as in the number 4, not the word for, doesn't exist, return tree is empty, right? So why don't we try this now? Run program. Okay, so now let's say py, actually we need to do this first. So let's say starting node is equal to tree node, and we'll pass it a value of 4, just like in our example, right? And we'll say starting, or we'll just call it binary tree is equal to tree, and we'll pass it starting node. And then we'll call binary tree dot traverse. Okay, since our tree is empty, actually and we can do this, right? Hopefully that makes sense. And we don't need this anymore. Okay, so let's just remove that. So we create an empty tree and then we try to traverse it. So our expected output should be this because we don't have a root right now. Right? Py bst.py. Name value is not defined. Line 10. This needs to come here. And this needs to be here. Maybe some of you noticed that before I did. And instead of returning, or we can keep it like, actually let's just do this. Tree's empty, so this is working now, right? So if we don't have a root, which in this case is true because we never set the root of our tree, then we're just getting back tree is empty, right? Okay, so now else tree is not empty. And just to satisfy those of you who were bothered by the uppercase, and no uppercase in the other print statement, tree is empty. And this time now let's say starting node is equal to tree node with a value of 4, and then we'll say starting node. And now we should see here, instead of tree is empty, tree is not empty. Okay, so this is working now. Fantastic. And we will come back once we've actually handled insertion and do the traversal. So we'll just come here and we'll say def insert self value to insert. Okay, so let's think about this. We know, and let's refresh this. So let's say we start here and we have our root with the value of 4. This is our tree's root because that's where the tree starts from. It's the starting node of the tree. And let's say now we want to insert a 2, right? So this requires a little more theoretical knowledge, but if you're interested in that, I'm not going to explain that here because that's not the purpose of this video. This is just a programming challenge. So we know that the left child of a node always has to be smaller. So we know we want to insert, so we'll just say insert. So we want to insert like a 2, right? Okay, so we look at this node, our starting node, and we say, okay, is 2 bigger or smaller than 4? It's smaller, right? So since it's smaller, we know that we're going to need to put it to the left. Okay, does that make sense? So cur is equal to self.root. So we're going to start always at the root of our tree, right, which we're now calling cur, right? And we say while there is no cur.left or not cur.right. So we're saying if there's no left child or no right child, actually this would make more sense if we say while cur.left. So while we have actually I have to pee real quick, and also I want to think about this for 1 second. Okay, so I went pee, but I didn't actually think about how to do this because that kind of ruins the point of the video, doesn't it? So this loop, if we say while not cur.left, or while cur.left and cur.right, right? So let's say while not cur.left, or actually we need to traverse until, right? If not cur.left and cur.right, pass elif not cur.right and cur.left, pass elif not cur.right and not cur.left, pass.
Do you know what's literally crazy when you message me
So,
when I was driving, and in my head I was
okay, so this is kind of a little weird to think about.
and I just was playing your whole like 2 hours.
So we say while, so certainly it's this, right? And it's going to stop executing after this iteration. And we're going to say if value to insert is less than cur.val, elif value to insert is greater than cur.val. So let's think about this first case, right? If the value to insert is less than current.value, and let's just say while cur here and simplify things, and let's just do this to make this all simple. Okay, while cur, if value to insert, so let's say we start here, right? And we want to insert a 2. If value to insert is less than cur.val, if cur.val, if not cur.left, so if the value is less than the node we're currently on, doesn't have a left child, we can just insert it right here, can't we? Right, so we can say cur.left is equal to tree node value to insert. Okay, similarly, we can take the same idea for the right child. If not cur.right, tree node value to insert. Okay, so now we've handled the case where, like, for example, so let's say, like, we didn't have that perfect scenario. So let's say, like, this is our tree. Three, right? So we start here, and we say, okay, the value is smaller than our, like, the value we want to insert, which is a 2, is smaller than 4, but we do have a left child. So in that case, we just want to travel down that left subtree. So instead of, now we want to move from here, right? And now we want to be here, right? And now we're at the next iteration of our loop, and now we say, okay, we make that same check if the value to insert is less than this node, and there's no left child, which in this case now there isn't. Now we set cur.left to be 2, right? And I think we can do the same thing here. Else cur is equal to cur dot right. Okay. So I think this is, we're not going to handle the case where we have duplicate values in the tree, because I think for a binary search tree you have unique values. I could be wrong, but this might work anyway. Okay, so let's think about this. So we start at the root, and let's just follow through our algorithm and insert 2 values. So let's say we want to insert a 3, a 2, and a 5. So let's follow our pseudocode. So we say, okay, cur is the root, so this is cur. Right? We said we're going to insert a 3. So we start here, we say, while there's a current root, if the value to insert is less than current.value, which we're here, if there's not a left child, which there isn't, set cur.left to a new node, the value of the value that we want to insert, right? So that's 3. Okay, so now we're done with that. Okay, so now we've taken care of that. Now, next time we want to insert a 2. So we say if value to, while cur, we start at the root again, right? If the value to insert is less than current.value, it is. If there's not a left child, which in this case there is, we have to go to this else here, which says cur is equal to cur.left. So now this cur pointer moves to here, right? Okay. And then that's one iteration of the loop, right? And then we start over again. We say if the value is less than the current dot value, the value we want to insert, which is a 2, right, is cur, right? And then we say, is there a left child? There's not. So now we follow this line and set the current dot left child to this new node 2, right? Okay. And then we finish that loop iteration. And we've inserted that value, right? So now 2 is inserted in the correct position. Now we say 5, and we follow the same logic. So we start here. If the value to insert is greater than current.value, which current initially is root, right? It is. 5 is greater than 4. Okay. Current.right, since there's no right child, we just go ahead and insert right here. And we say 5, right? So now we've inserted all of these nodes into our tree, and it looks like it's populated correctly because we follow all the rules of the binary tree. Each parent has at least 2 children, and the left child's always smaller than the parent, and the right child's always bigger than the parent. Okay, so I think that this insertion algorithm is going to work, and it's pretty short, so I'm happy with this. And I just really need to So in order traversal visits the left, then node and fire to the right. So hence goes traverses in order of the values. So what I'm going to say here is we're going to say again cur is equal to root. Actually, we're going to do this iteratively. So we're going to say stack is equal to root. This is like my lead code muscle memory again. Well, stack. Current is equal to stack.pop. This is depth first search though. I think we can still do this though in order traversal. And we don't have to specifically have to do in order, let's just do any traversal, honestly. So this is done. This is done. We're just gonna change this to be anything. Right? Cur is equal to stack.pop if cur. Stack.append. Cur.left. Print. Cur.val. Stack.append. Cur.right. Okay. I think this is right. Print. Traversal. Output. Okay. So now down here. And let's do what we said here. Let's insert a 3, then a 2, then a 5. 3. Insert 2. Dot insert 5. And then let's traverse the tree. And it looks like we have an infinite loop. Maybe this is the issue. Okay, so that was the issue. So we see 4, 5, 3, 2. So it looks like it is inserting nodes correctly. I think it's just our traversal that's weird. So let's just take a peek some more. So yeah, let's just say, sorry, one sec. Okay, I got a call. Apologies for that. So we can do this recursively. So we can say like self.traverse current if not current, else self.traverse left dot left return print cur.val self.traverse cur.write. And now let's add a def get root self return self.root and tree.get root. Okay. I think this will work. 2, 2, 4, 5. So it looks like it's now traversing in order, which is what we want. Print traversing tree in order. Okay, so now we have 2, 3, 4, 5, right? Which means that it's in order, right? In order of values, which means that one, the values that we're inserting are getting inserted correctly in terms of the rules of left and right values, because this in order wouldn't work if the left and right children did not follow the binary search tree rule of the left child having to be smaller than the root or its parent, and the right child having to be bigger than its parent. The traversals aren't working correctly. It's recursive, which is not super optimal, but that's not really the point of this video, right? Okay, so now we've done traversal. And deletion. No. One more step. So we can do a depth first search, which is what we were gonna do for traversal, but let's use a DFS for deletion instead, because I think that makes more sense for deletion. Def delete self value to delete. Okay. Stack is equal to self.root, right? Well, stack is equal to stack.pop. So how do we delete a node from a tree? Say we want to delete this 3. If we just delete this node, it also deletes this child reference, doesn't it? But we don't want to lose this 2, do we? We want to keep the 2, right? Also have to be again. I'll be right back. Okay, so very unfortunately, something has come up and I have to pause the video here. But I think in our next challenge, in a couple of days that we'll do, we will tackle this deletion problem and then solve a new problem. So I'll leave this as an exercise right now to the viewer to figure out this delete method for our tree class. But until then, I will get back to this. And I think this is the block comment in Python. So yeah, I'm going to end it here. Thanks for watching and goodbye.